Yeah, thanks. Yeah, thank you for the invitation. It's good to see some people who I haven't seen for a while, especially haven't seen in person for a while. So a lot of what I'm going to talk about is joint with Julian Chaidez. He's a symplectic geometer. My background's in algebraic geometry, but even though there's the number 2 in the title, there are really kind of 3 threads to this talk. There's sort of a combinatorial thread, a symplectic thread, and then also kind of linking the two, there's going to be an algebra geometric thread. And so I'll try and keep all these things in kind of a fruitful tension. But if it's becoming unclear or you'd like me to just specify where we are and how things are fitting together, please feel free to ask. So the basic kind of object or setup that I'm going to work with is I'm going to be considering a region omega in Rn, some convex region. And there are kind of 2 types of such thing that I'm going to think about. So one type, we'll have it so that omega is a polytope. And 2, that the boundary of omega is rational slopes. And what I just mean by this is that the normals to each of its facets are rational. So some multiple, the real multiple of them is a lattice point, or it's a lattice vector. And so such objects I will call moment polytopes. The other class of regions that I'll think about will not be polytopes. Just say A and B for this. Not in general polytopes. They will live in the kind of positive orthan. And I'll draw a 2D picture, but hopefully it gets the point across. They will look kind of like this. So the key features of this diagram that I want to emphasize is it has 2, well, in this case 2 in general, n facets along the coordinate hyperplanes meeting at the origin, or any other kind of subfaces there. So it lies kind of in the corner of the positive orthant, and then this outer boundary region just ensures that the region is convex. Okay, so like I've kind of drawn, I'm not assuming that this region is a polytope. I will make this assumption at a later point, but these are the 2 sorts of regions that I'm gonna look at. And this type of region I will call a convex domain. Okay, and we'll do some examples, kind of interesting examples in a minute. And then notice, let's say my region was polytope, or even at least just looks like a polytope near kind of one point, near this point, up to the action of the kind of integral affine group. This just means that I have a smooth vertex. So it's actually not too much of an assumption, but for the symplectic stuff, it's going to be important that this guy is based at the origin. Okay, so these are the 2 sorts of objects that I'm going to talk about, and to each of them I can associate some spaces, some interesting kind of geometric spaces. So some geometry. So I'm going to consider Cn, I'm going to consider it as a symplectic manifold in kind of the standard way. This has a torus action, just by rotation in each coordinate, and that produces for me a moment map to Rn in other words, to the Lie algebra of this torus. So really here, like I say, when I'm thinking, I'm in the symplectic picture right now, I'm thinking of this as a symplectic 2n manifold, and this as a Hamiltonian group action. And so with this setup, actually, let me just also write for you what this map is really doing. Up to the choice of scaling on the symplectic form on the moment map, this map is essentially, it's just the absolute value squared map. And so really this lies in the positive orthent. And that is the reason for this positive orthent condition here. Okay, so given this setup, let me draw a picture for you again in 2D of what the pre-images of this moment map look like. So this picture I'm drawing right now is R2, the Lie algebra of the 2 torus. And out here, the pre-images are just the empty set. If I pick a general point or any point in the kind of strict positive orthant, the pre-image is a 2 torus. If I pick a point on the boundary, the pre-image, or on the axis, sorry, the pre-image is a circle, and then the kind of most degenerate orbit is above the origin, which is just a point. So, definition, let omega in Rn positive orthant be a convex domain. So this is a convex region satisfying A and B in my prelude. Then X omega, which is just defined to be the pre-image of omega under the moment map, is a convex toric domain. Okay, so convex toric domains are, these are so these are toric symplectic manifolds. I guess 2n manifolds. Okay, so let's just see some examples. Actually, let's just scroll back to this like construction of this moment map, where really taking the pre-image of some convex region is just sort of prescribing some constraints on the absolute values on the modulus of my of the coordinates, basically. And so it's not so hard to see from that kind of direct picture some examples that actually a lot of very classic symplectic manifolds can be obtained in this way. For example, if omega is just a right triangle like this, which is equilateral, then x omega is what I'm going to denote E2NA. It's a ball of radius with my kind of scaling convention of radius a over pi, but I'm going to ignore this pi factor and just call this B2NA. Okay, if I modify this slightly and instead allow myself to have a triangle with some eccentricity, x omega is an ellipsoid. And so I'll write this one down. So this is an ellipsoid with up to scaling by pi radii A and B. Okay, and then kind of the last example, which I'm going to refer back to at various points, if I pick a rectangle, I get a so-called polydisk. Okay. So there are lots of classic ones one can get. Let's just also know that these spaces can also be pretty weird. Kind of spaces like this, where it's like, well, I'm not really sure how to interpret this apart from the description that I've already given. Okay, so these are the prime sort of symplectic spaces that we're going to be looking at or using. Okay. Now, in algebraic geometry, a story which I'm sure many of you are familiar with, to what I'm calling a moment polytope. One can associate a polarized toric variety. Let me also say possibly singular. Which I'll denote by y sub omega, a sub omega. I'm not going to spell out this construction part because I suspect it's familiar to many of you. But this I will write down, or I will describe its moment map. So in particular, I can kind of put my symplectic goggles back on and view this polarization, view this ample divisor as giving me a symplectic structure with some moment map from y omega to Rn. And what does this map look like? Let me just draw you the fibers, and again, I'll just do it in 2D for convenience. If my polytope, wherever it's living, regardless of its relationship to the axes, I can think of this as the fiber over an interior point is going to be a full dimensional torus. The fiber of a kind of generic boundary point is going to be a codimension 1 torus. And then going all the way down to kind of the most degenerate fibers, where the fiber over a vertex will just be a point. Okay. So notice that this kind of difference between this picture and this picture is going to be one of the things that we're going to exploit, where in particular, this picture really sees the axes, whereas the other picture does not. Okay. So I'll try and keep scrolling to a minimum. Okay, so let's just write down some familiar examples. Actually, I'm just going to write down the list of examples that I just talked about. So for this omega.
May I quickly?
Mm-hmm.
May I interrupt you? Sorry. Just to make sure that as an algebraic toric geometer, so your polytopes, your moment polytopes, live in the lattice of characters of your torus.
That's right.
Okay.
Yeah. Thanks for clarifying that. Yeah. Right. So when I write this y omega, this is the y associated to the normal fan, either in or out a normal fan of omega, and that's of course why I needed to assume that my my normals were rational.
Thanks.
Of course, yeah. So if I pick this polytope, I'm just going to fix my stuff on the origin to kind of match the previous discussion. This is P2 with polarization OA, or A times the hyperplane class. If I pick my kind of eccentric triangle, I obtain, I'm going to be a little bit careful here, or maybe I guess I'm going to be a little bit not careful here. This is a weighted projective space polarized by, again, some multiple of the natural O1. Depending on the kind of co-primeness of A and B, I might have to be a little bit careful. But for example, let's just, if I was assuming that A and B here were co-prime, what I've written down is totally correct, where D would be AB. And then 3. AB, this produces for me P1 cross P1 with OAB. Okay. And for example, the kind of the weird domain that I drew before, by the weird domain I mean the one that was like this, say. This does actually have an analog in algebraic geometry as a kind of infinite blowup, but I'm not going to talk about that in this talk. It does, yeah, this construction is in a paper of mine from earlier this year, and I'm happy to say more. I'm happy to say more in the questions afterwards, but I'm not going to address it. It's not relevant to the current story. Okay, and so the key observation, or the reason that I kind of belabored these examples, the key observation that we're going to use is that if I look at the interior of one of my x omegas, so this is like the open ball, this lives inside y omega even after I take out the support of my polarization, the support of my divisor, a omega. So for example, the 4-ball of radius A is kind of classically known to lie inside P2 minus. I've written AH here just to kind of imply that this is P2 with that has area A, has volume A. The H is really the important thing here. That a ball is symplectomorphic. In this case, actually equal to P2 without a hyperplane section. So let me just, yeah. And, oh, sorry, I actually mean equal to open ball. Okay. And so this is a key observation because it's one of the kind of main tools that I'm going to use to move between the symplectic and algebraic worlds. So this is a symplectic object, which is well studied from the point of view of trying to embed symplectic, like one symplectic thing into another. And this is some kind of nice algebraic object that we have a good handle on its geometry. And so the interplay between these two elements is kind of the main driving force behind a lot of what I'm going to talk about. Okay. So maybe I'd pause for any questions so far.
Seems everything clear.
Great, thank you. Okay, so let's introduce the two widths. So let's start with the lattice width. So for a polytope, omega in Rn, polytope, we're just going to straight out define the lattice width, which I'll denote by LW of omega. It's just defined to be, it's a min max. So it's the min over L in Z2, or in Zn, I guess, without the origin of the max of pairs of points in omega of just the pairing inner product of L and P minus Q. So it's pretty clear that P and Q should lie on the boundary of omega for this to work. How to think about this sort of intuitively or combinatorially? Essentially picking an L is prescribing a direction, or say a normal direction, and what this max is computing is essentially what is the thinnest slice that my polytope fits inside. So some polytope like this, and what I'm essentially asking, if my L looks like that, I'm essentially asking what is the thinnest slice that I can fit my polytope inside. So let's just do an example real quick. This is a very useful example for what we'll do. Let's look at that rectangle. So we're using the min of L1, L2, where not both of these are 0, of the max of L1, let's say P1 minus Q1, plus L2, P2 minus Q2. Well, the biggest possible thing that the x coordinates could differ in is A. The biggest thing that the second coordinates, the y coordinates, could differ in is B. So this is just the min of L1, L2, A L1 plus B L2, and this is just equal to the min of A and B. Okay, so I'm not allowed to have them both be 0, so the next best option in this case is to have one of them be 1 and one be 0. Okay, so that's the combinatorial width. Let's define the symplectic width of interest. This is the Gromov width. So let X be a symplectic 2n manifold. Okay, so X comes with a symplectic form that I'm not specifying. I'm not including the notation, sorry. Define the Gromov width, CG of X, to be the sup of all positive A, such that a ball of the same dimension with this kind of symplectic radius A symplectically embeds into X. So what I mean by symplectically embeds is this is a smooth immersion, or smooth embedding that respects the symplectic structure. And by respects, what I mean is if you pull the symplectic structure back to this, you get the kind of original symplectic form. Okay, so essentially, heuristically, what is this? Essentially, it's the radius up to maybe some factor of pi. It's the radius of the largest ball that embeds into your space X. The largest ball may not exist, so that's why it's a sup. But intuitively, we're saying how big is a ball that we can fit into X? How big is the sort of roughly the biggest ball we can fit into X? Okay. So let me draw the same picture again. And this time, let me superimpose. So let's just assume that B is less than or equal to A, as I've kind of drawn it. Then I can fit this triangle into this rectangle. Notice that the kind of light blue triangle, let's call that delta, and the purple rectangle omega. X delta is, in this case, the four-ball of radius B. And I've just expressed it as a subset of X omega. In particular, there is a symplectic embedding from this ball, X delta, into X omega, which we saw was on the polydisk. Maybe actually I'm using a different color just to. Okay, and so what does this show? It shows that we kind of have a trivial ball lying inside X omega. And so it shows that CG of the polydisk is at least B, which by my assumption that B is less than or equal to A, is the min of A and B, which in this case is the lattice width of omega. Okay, so I haven't computed the Gromov width of the polydisk yet. So also notice that, in fact, because I can view sort of the open polydisk as a subset of P1 cross P1, where I've equipped it with sort of an appropriate symplectic form, this actually also implies that the Gromov width of P1 cross P1 with this kind of weighted symplectic form is also greater than or equal to B. Because a ball that I can fit inside omega, at least like this, where you kind of notice it's avoiding these this boundary zone, I can still fit that ball inside P1 cross P1. Okay. And so it turns out, right here we had the Gromov width being greater than or equal to the lattice width. This is actually a little bit deceptive in this example, because actually the conjectured relationship is the opposite. This is a conjecture of Averkov, Chaidez, and Ben Nill from 2019, which I'm going to state slightly differently. Let omega be a moment polytope. Then the Gromov width of the toric variety y omega is less than or equal to the lattice width of omega. Okay. So in particular, this would imply immediately that the Gromov width of P1 cross P1 with OAB is actually equal to B. But that's also something you can just check directly. Okay. So this is our conjectured relationship between the two widths that I've introduced, this combinatorial width and the sort of symplectic width, but of this algebraic space. And so actually they do some work in this 2019 paper and show that a key step in trying to prove this would be to show monotonicity of the Gromov width under inclusion of polytopes. So a key step would be to have if omega lies inside delta. And notice that this is not immediately obvious in really any way, because if I have an inclusion of polytopes, it's not at all clear, and I'll even draw something like this. It's not at all clear that, I mean, there isn't in general a map between the purple polytope and the light blue polytope, and so there's not really a natural way that I can try and move a ball from one space into the other. Okay, so key step required, let's say. Okay. This I should say, this kind of monotonicity, which I will refer to through the rest of the talk as Gromov monotonicity. This is an open question in symplectic geometry. And notice, for example, this is immediately clear for the case when omega and delta are convex domains, and we're interested in the x omegas instead of the toric surfaces y omega and y delta. And I'll say more about that in a minute. The theorem of Julian and myself from I think maybe we proved it in 2020. The paper may have come out in 2021. Is indeed that this conjecture is true in dimension 2. And there's a very slight caveat, at least when omega has one smooth vertex. Okay, in other words, when the toric surface has at least one smooth torus fixed point. And it's possible we can use our methods to get around this assumption, but we haven't got that so far. Okay, and so this is just dimension 2. The main point and the thing that I kind of want to get at, hopefully towards the end of the talk, is that it presents a kind of a methodology for approaching this question, at least in special cases, in higher dimensions too, using this kind of three-way interplay between combinatorics, symplectic geometry, and algebraic geometry. Okay, and so like I said, the main thing, or really the main, I guess the main corollary that we proved in our paper was Gromov monotonicity. If omega and delta, as above, have at least one smooth vertex, then CG y omega is less than or equal to CG y delta. Okay, and so yeah, there are these two steps in proving this conjecture in 2D. One of the steps is proving monotonicity. The other step is a sort of reduction argument once you have monotonicity to reducing it to a calculation that we've already done. In fact, it's to reducing it to this calculation and this calculation with equality, and that's something that follows immediately from Gromov's famous non-squeezing theorem. So I'm not going to talk about the reduction step, but I will talk about proving Gromov monotonicity. So I will talk about this result. Okay. Okay, so before we dive into talking about the proof, talking about the kind of interesting new structures that come out of it or that we use to prove it, are there any questions about these results, conjecture, anything that I can clarify to be helpful before we jump into that? Okay, cool. So like I said, the strategy has two parts. First part is prove Gromov monotonicity. And how do we do that? We use some embedding obstructions in symplectic geometry that have some nice avatars in algebraic geometry. And this kind of nice relationship means we get to pull stuff from the some powerful embedding results in the symplectic world into the algebraic setting. And then the second, like I said, is reduce to P1 cross P1 and apply Gromov non-squeezing. And this step I almost certainly won't talk about. Okay. So let's talk about Gromov monotonicity. Okay. So let's let me introduce some invariants, the kind of main players of our approach. I'll introduce them three ways: a symplectic way, a combinatorial way, and an algebraic way. And then we can, and then I'll talk about how they're related. So first of all, if X is a symplectic four manifold, we can associate to it a sequence CKX, where, roughly speaking, I'm not going to define this one fully formally, roughly speaking, CKX is the minimum area of a set of Rabe orbits of some vector field, some special distinguished vector field called the Rabe vector field, with index equals to k. Okay, so I'm not really going to talk about this construction. The only important thing, I guess, to keep in mind is that this ck, of course, this area is with respect to the symplectic form on X, of a set of these of kind of certain orbits on a symplectic manifold. And there's a point of view which is kind of, again, one of the main bridges between this world and algebraic geometry, is that one can view these Rabe orbits as being the boundary of certain curves inside the interior of the symplectic manifold. And we just saw from earlier on how the interior of the symplectic manifolds we're looking at are related to some algebraic varieties. Okay. So I don't really want to talk about this in much more detail. These are called the ECH capacities, and they're introduced by Hutchings in 2011. Okay. And the main value, well, there's kind of two main reasons that I guess they're prominent and helpful. The theorem, just for four manifolds, is if you have a symplectic embedding from X to X prime, then CK is less than or equal to CKX prime for all K. Okay. So, in other words, these are embedding obstructions. Version 2, this is, say, the combinatorial version. So let's consider a convex domain. Let's say a polytope, which is a convex domain. And let's say we fix some other vector v. We're going to define a pseudonorm, which I'll denote by norm of v sub omega, and it's defined as follows. You find the point on omega to which v is tangent. So there might be a vertex, and by tangent, what I really mean is that the polytope lies entirely in the right half space, kind of subtended by this vector. Call this point, which might be non-unique, but it won't matter, call it PV. Then the so-called omega norm of V is defined to be the determinant of the matrix with columns V and PV. Okay. So it's essentially what it is it's sort of just a weighted pseudo-norm on the on R2, which is kind of weighted or controlled by this omega. Then we define, say, ck omega. This is the min over convex lattice paths the omega norm of the path such that the path encloses k plus 1 lattice points. Let me draw a picture to kind of make this much clearer, hopefully. A convex lattice path is a path starting somewhere on the y-axis and then is piecewise linear until a piecewise linear path that encloses a convex region lands on the x-axis, and the condition is asking that inside this region, this convex region, there are exactly k plus 1 lattice points, and the quantity that we're minimizing is the omega norm of this path. It's just the sum of the omega norms of each of these vectors. Okay, so it's a little bit weird. Again, I wanted to show you this just to give you a sense of the kind of combinatorial side. I'm not going to use this definition too much, but I wanted to give you a sense of what these kind of three invariants look like. You might notice that another way you could have phrased this was by having by counting over polytopes or polygons in this case, with two edges on the coordinate axes that include k plus 1 lattice points and have sort of omega perimeter, some certain amount. And then thirdly, if YA is a polarized surface, let's say it's sufficiently non-singular, Q factorial is enough. Define CK, I'm gonna give these ones a name, CK alg of YA is defined to be the min over nef divisors on Y. That is Z cycles of coefficients in Z that are nef of D dot A such that, well, let me write it like this, such that the Euler characteristic of D is at least K plus chi over Y. Okay, so what really is this minimization problem saying? Again, d dot a we can think of as an area. A is prescribing some sort of area that we assign to curves. D, I could have, instead of writing Neff divisors, I could have written movable curve. Really, we're interested in areas of some curves, some algebraic curves. And then this condition is essentially saying that with big enough moduli, to make it a little bit clearer, if YA is kind of in the situation that we care about, is toric, then ck alg of y omega a omega is the min over Neff divisors d dot a omega, such that we have de Maizière vanishing, and so this is chi is just h naught. And so what we're really asking is we want to minimize kind of area of curves or divisors with big enough moduli, big enough linear series. Okay, so these are these three invariants: this symplectic invariant, this combinatorial invariant, and this algebraic invariant. And the theorem of, let's see if I remember all the names, Christopher Gardner, Choi, Frenkel, Hutchings, Ramos in 2015, and then me in 2019, is that these three, these three invariants agree when omega is a rational sloped polygon that is also a convex domain. Okay. And remember that in the case of rational sloped polygons or rational sloped polytopes in general, being a convex domain really just means that you have a smooth point, a smooth torus fixed point. Okay. And the sort of main point to draw from this is that ck x omega is encoding embeddings into x omega, and ck alg y omega a omega is kind of encoding algebrogeometric information. But we know that these two things are purely algebrogeometric information. Okay. And so the theorem, using the fact that these invariants coincide, the theorem of Julian and myself is that an open ball embeds inside toric surface y omega if and only if the ECH capacities of the closed ball are less than or equal to the algebraic capacities of y omega and a omega. Okay. So this direction is essentially clear. There's a little bit of work to do. This direction follows from some very strong embedding results that symplectic people proved for x omega. Let me state that, and then I'll prove this theorem. So one of the main things that we use is a result of Dan Christopher Gardner, who says that an open ball embeds inside x omega when omega is a convex domain if and only if ECH of the closed ball is less than or equal to ECH of X omega. Okay, and in general, there's nothing really special. Well, there's something special about a ball, but it's not too special in the sense that this also holds if you replace a ball with any star-shaped domain. Okay. So let me prove this theorem just to give you a sense of what these arguments feel like. So one direction is sort of obvious in the sense that if we have an embedding of the open ball inside y omega, well, let me say it like this. If we have an embedding of the open ball inside y omega, Julian and I prove a different theorem using Seiberg-Witten theory and some birational geometry to deduce that the ECH capacities are bounded above by the algebraic capacities. So actually, yeah, maybe I should be careful and say this is not obvious. The reason you should expect this is because you have this open thing embedding into y omega, and we've seen that when you take out the amplitude divisor a omega, you just get x omega back, and so that's why you would expect to have an inequality. To show it in general, we use these kind of more sophisticated mechanisms to show actually that the CK-alg are embedding obstructions. The other way, the kind of constructive way, which is kind of more relevant for us, has the following. So suppose that the ECH capacities of the ball are less than or equal to the algebraic capacities of y omega a omega. Well, because these guys are equal to the ECH capacities of x omega, okay, just because this and this are equal. And so that implies, by this result of Christopher Gardner, this very strong result, this implies that the open ball embeds inside x omega. Actually, one can set this up to embed inside the interior of x omega. But now the interior of x omega is a submanifold of y omega. So the open ball embeds inside y omega, and hence very good. Okay. So the point of this theorem is that ball embeddings into toric surfaces are completely controlled by knowing these ECH capacities of the ball, and they're very easy to compute. And the algebraic capacities, these like optimization problems over Neff divisors of y omega. And so as a corollary to this, one obtains that if omega is inside delta with, say, one smooth vertex, then the Gromov width of omega is less than or equal to the Gromov width of x omega is less than or equal to Gromov width of x delta. And the main reason this follows is that we've seen from the previous result that all we would need to know is that the algebraic capacities are monotonic under inclusion, and actually we can guarantee this proof. Just need that the algebraic capacities are monotonic under inclusion. A delta. This follows. This follows from the fact that the algebraic capacities. I'll ignore the omega just for the moment. And this follows from the fact that they agree with the symplectic capacities. And in the symplectic land, if you have an inclusion, just by the fact that we set up x omega and x delta to be pre-images of omega and delta respectively, these guys naturally live inside each other. And so their capacities have to be monotonic. Okay, and so it kind of comes for free from this translation theorem that the algebraic capacities are monotonic under inclusion because they provide a complete obstruction to ball embeddings. That means that the Gromov width has to be monotonic. Okay. And so that's a sketch of how we prove this. And then just in my last minute, let me say that that very strong embedding result that we were really relying upon only works in dimension 2 or real dimension 4. Right now, there's been a lot of work over the last year coming up with some new embedding obstructions that work in higher dimensions that may have a chance in special cases, at least, of pinning down the Gromov width. In other words, completely pinning down ball embeddings. And Julian and I have a paper coming out, hopefully in the next month or so, which provides some algebraic analogs to those invariants, at least in dimension 2. And so if we're able to extend that, then this strategy is one that we hope will work to prove Gromov monotonicity, hence this lattice width bound in higher dimensions also. So thanks for your attention. I'm happy to discuss more. Thank you.